Hello, I just wanted to make a video going over the important parts of the note. So let's do that. So we're doing acceleration, and we're on acceleration day 2, and we're working on models of acceleration. Let's see. And here are the notes. So these are models of accelerated motion is what the book calls it. I should have wrote it on there. Models of accelerated motion. So what is a model? Well, the equation is a model that predicts the position x at any time t. So that's this first one here. Instantaneous position and accelerated motion. So before we had this equation, velocity times time is distance. It still works. And that is this blue section here on this graph. So this is the really cool thing about physics, math, science, is that they're all connected in a complex and beautiful way that I barely understand myself, right? And some people grasp it a lot more. Like it's really a beautiful, complex thing that is almost indescribable, ineffable. Some people say. Because we're describing reality, and reality as we know it, we don't understand very much of it. So that's why it's a very interesting subject. So what happens is a scientist will make some experiments, and he'll get some data, he'll graph it and look at it, and he comes up with a graph that looks like this. Then he's like, well, equations can describe these graphs, right? We all know that from algebra. You have an equation, and then you put it in, and you can graph what it looks like, and you get a bunch of results and points, right? So once you have that, then you could go back and make your equation. And so this equation represents this graph, right? So when we put numbers in, we come of this equation, we come up with this graph. When we have this graph, we can come up with this equation. It goes both ways, right? So this equation will tell you the position of an object that's accelerating, right, at any time. So you take the initial position, and then like this is our equation from the speed, right? Velocity is distance divided by time, or you can say this position is equal to velocity times time. And so this blue part is represented here. But that's the thing, is like this is for a constant speed. It's just flat, right? But now we know that if an object is accelerating, its graph is at an angle, right? And how steep your graph is, that's more acceleration or less acceleration, right? So this is represented by this triangle. And you can even recognize the formula for area of a triangle, right? 1/2 base times height. So here is 1/2 base times height. We see 1/2 the base, which is time, and then velocity is acceleration times time. So then we put those together, and we get that formula, 1/2 AT squared. So that's where it comes from. So that's why this is how we came up with this formula. I think that's a really cool visualization of how we got an equation from the graph. All right, so that's for getting position. Whenever they ask for a distance or a position at time t, you use this equation. If they ask for velocity, we're going to use this equation. So initial velocity is here, and then we have, see, acceleration times time will get us that final velocity. See, final velocity is your initial velocity plus acceleration times time. That's where this comes from right here. So here are the units. This is important. So this equation will solve for your final velocity. Whereas this equation up here solves for a distance, which is not on this graph, but you can get a distance, right? This formula solves for velocity on the graph. So we can get the final velocity at any time t if we know a, right? So here's some examples. This is using the guess method, like we've talked about before, right? Your givens, unknowns, equation, substitute, solve. I should do one of these. Let's see. Let's do one of these. Let's do this together. A cart travels at 1 meter per second, and he reaches a hill and accelerates down at 0.5 meters per second squared. What is the cart's velocity 3 seconds after it starts accelerating? Okay, so let's draw a picture. So we have a hill, and then he's going to come down. We have a cart of some type, maybe a shopping cart, and this kid is just having a good time. He's about to go down. So let's do what's given. 1 meter per second, that's the velocity. So that's his initial velocity, right? So VI is 1 meter per second. He reaches a hill and accelerates down. Okay, so they're giving us an acceleration, and we know it's an acceleration because they say it accelerates, but also it has the units of meters per second squared. So 0.5 meters per second squared. What is the cart's velocity 3 seconds after it starts accelerating? Okay, so then they give us time. So what's unknown? They want to know what is the cart's velocity? So they want to know final velocity. So what equation are we going to use? So they want to know the final velocity. So we go to our notes and we say, oh, it's this one. It's not this one because this gives you a position, a distance, right? This one will give us our velocity. All right, so now we're going to substitute. So VF equals VI, which is 1 plus 0.5 times 3. So I'm going to put that in my calculator. If I can find one. A bunch of pencils. I'll use my phone calculator. Almost out of coffee. Getting hungry. It's almost time for lunch. Let's see. All right, so 1 plus 0.5 times 3. I guess I could have done that in my head. 2.5. And it's a velocity, so the units are meters per second. Let's make sure that did I get it right? Yeah, 2.5 meters per second. Let's do another one. So we're going to do example 3. because it's the other formula. All right, a bowling ball rolls with an initial velocity of 25 meters per second and decelerates. So this one, the ball is slowing down. How far does it travel in 10 seconds? So we have a ball, bowling ball, and it's rolling along. Initial velocity of 25 meters per second. And then we know, so what else is given? So given, they gave us velocity initial. And they gave us an acceleration, a deceleration of negative. So this ball is getting slower. So your final answer should be smaller, right? How far does it travel? Okay, so we want, in 10 seconds, we have the time. So what's unknown is distance. How far does it travel? So we go get let's get our formula. X equals x naught plus v naught t. X equals x naught plus 1/2 at squared. I always forget. Let's see. 1/2 at squared. All right. So now I'm going to sub. The initial position is usually 0. So initial velocity 25 times 10. So see, this is, if he was going at a constant speed of 25, he would go 250 meters, but he's decelerating, he's slowing down. So we're taking into account that acceleration. So instead of writing 1/2, I'm writing 0.5 times negative 0.5 times 10 squared. So I know that's 250. Let's see, 10 squared is 100 times 0.5, which is 50, times 0.5 again is 25. So that's actually a negative 25. So my answer is 225 meters. So that's how far this ball went. So let's see, let me make sure I got the answer right. Yeah, 225. So that's how it's done. And that's it. So I'll just go over this in class, and I'm going to do a video of the practice problem.